be a number field with at least one real place. Let E over K be an elliptic curve. Then E mod P or E mod V is supersingular for an infinite set of places, of primes. Okay. So, well, what can be said about K3s? Following theorem is now true. So let K be any number field. All right. So in fact, let me just say a quick note. I'll be talking about arithmetic settings. So for the most part, I'll be working in characteristic P. So I'm going to call that the arithmetic characteristic P setting. But I'll also mention results in the number field setting, which I'm going to call the mixed characteristic setting. So if you have K a number field and a K3 surface over that number field, then there are infinitely many primes such that the Picard rank of X mod V, and then you base it to the algebraic closure, is bigger than the Picard rank of the K3 you start off with. Now, okay, let me quickly say who did what. So in the case when your K3 surface is a Kuma surface associated to a product of two elliptic curves, Francois Charles proves this theorem. This theorem was not stated in this language. It was stated in the language of starting off with two elliptic curves that need not be isogenous in characteristic 0. And then he proves that there's infinitely many specializations, modulo which they admit isogenies. And that has exactly this consequence for Picard ranks of the associated Kuma. In joint work with Tang, we do the case when X is the Kuma associated to an abelian surface where the abelian surface has real multiplication. And in joint work with Ananth Shankar, Tang, and Tayou, we prove this for when X is general K3 surface, but with the restriction that the Kuga-Satake abelian variety associated to X has potentially good reduction everywhere. And finally, Salim relaxes the good reduction hypothesis.
So why doesn't this theorem apply to the Kummer surface for E cross E without these theorem of any number field?
For any number field, why doesn't
Because
this?
your number field is any number field, right?
That's right.
So
Well, so if E is not, are you saying why doesn't L keys imply the case of Kummer of E cross E?
I think.
Sorry, I was confused about the question. Is the question why this doesn't imply L-keys or why L-keys doesn't imply this? For the
It seems to me that the cover surface of E cross E, the Picard rank jumps exactly when the E is supersingular.
No, that's not true. So it jumps. So if your E is CM, then that's true. If E is not CM, it jumps whenever E acquires CM. But E acquires CM at every prime. So this doesn't say anything about supersingular primes. Like if you were to calculate, if you were to start off with if you were to take an E cross E where E doesn't have CM, and if you were to take an E cross E where E has CM, and you take the two Picard ranks, you take the two Kumas and you take the Picard ranks, the CM case has a bigger Picard rank than the non-CM case.
Generic Picard rank.
Sorry, I'm just taking one elliptic curve over a field, over a number field.
Yes.
Let's say that in fact, let me take two elliptic curves. The first one is CM, the second one is not CM. Now, if you look at the Kumar of E cross E where E is CM, that's bigger than the Picard rank of the Kumar of E cross E where E is not CM.
Yes.
So if you start off with...
Because one has more endomorphisms than the other.
That's exactly right. So if you were to start off with an elliptic curve that does not have CM, well, mod P, it has CM at every prime P. Like every abelian variety over FP bar has CM. And so if you start off with an elliptic curve that's not CM in CAD 0, then at every prime P, its reduction, the Kumar of the reduction will have a bigger Picard rank than the Kumar of the elliptic curve you start off with. Simply because the elliptic curve does not have CM in CAD 0, but has CM in CAD P. So that's why this does not imply or need L-keys. Okay, other questions?
Okay. Yes.
All right, so my title has non-ordinary in it. So let me talk about the ordinary case. So now let me talk about the arithmetic characteristic P question. Well, so let me fix a curve over FP bar, and I'm going to work with a non-isotrivial family of K3 surfaces over that curve. And I'm going to assume that your X is generically ordinary. Okay, so then in this case,
It's a case 3. It's
Sorry?
a case 3.
yeah, K3.
Thank you.
Thanks, Olivia. Well, then we have the same theorem. There's infinitely many points on your base such that the Picard rank of the specialization is bigger than the Picard rank of the generic K3. And let me just,
When you say generic, you mean geometric generic? Yeah, geometric.
yeah, geometry. Yeah. Thank you. And in this specific case, Chai and Oort use the fact that the moduli is a product of two curves and the fact that you've got Frobenius on each coordinate to come with a really clever proof to show that if your X is the Kumar associated to a product elliptic curve, then the theorem holds. In joint work with Devesh Maulik and Jiang, we do the case when X is the Kumar associated again to an abelian surface. and Davish and Yunqing, we do this case for general X, but again under the good reduction hypothesis. And that I'm going to just say as C being compact. To be precise, we don't really need the family of K3s to live over a proper base. It's enough for the Kuga-Satake family to live over a proper base. There's a subtlety there, which I'll talk about at some point. But that's all we need. And in the same paper where Tayou, where Salim relaxes the good reduction hypothesis in the number field case, he also removes the properness hypothesis in the function field case. Right. Well, this is ordinary. What happens if your family is not ordinary? So the theorem is not true. There are counterexamples. Here's a somewhat silly counterexample. So if your family ended up being super singular, then the Picard rank of the generic fiber is going to equal the Picard rank of every single fiber. And that's going to be 22 or something, and this Picard rank cannot be seen in characteristic 0.
Isn't it isotrivial? It's theorem of.
So what do you mean by isotrivial? Do you mean like after replacing a basis constant?
Yeah.
No, it's not. It's not. It's not.
But what is the theorem of Renault? It's very close to that.
Okay, so let me tell you what it is in the case of abelian varieties.
Yeah.
If you were to take a family of super singular abelian varieties, then it's going to be isogenous to the trivial family. So if you mean by iso as an isogenous, then in some sense, yes. But this is in some sense not the most interesting example. It's sort of like having a positive dimensional family of CM abelian varieties. If you have that, then that's going to supply similar examples in whatever setting you want. Okay, so that phenomenon is interesting, but it's fairly well understood. And if you're like not surprised with that phenomenon, then this counterexample is not that surprising. Here's another example. And yeah, and as Elaine pointed out, you should think of this as being isogenous to the constant K3. Well, Picard ranks are, they don't see isogeny data, they're independent of isogeny. Here's an example of something that's not isogenous to the constant family. So take an elliptic curve over C that's non-isotrivial. So it's sort of, so the map from C to the modular curve dominates the modular curve. And now take ES, call this a supersingular elliptic curve, S for supersingular.
So S is a corresponding singular.
No.
No.
It's a proper noun. So ES is a supersingular elliptic curve.
Okay.
And S is just like a subscript denoting supersingular. So now you can, well, pull ES back to C. And now you can look at E cross ES. This is an abelian surface. Look at the Kuma. Now you can check, and I'll explain why later, but you can check that the Picard rank of this jumps precisely at those points of P, those points of C, where E has supersingular reduction, and therefore that's a finite set of points. that's finite. Well, you could also perhaps object to this by saying that, well, this is not true. This Kumar is not truly isotrivial because it's varying in one coordinate, but it's not varying in the other because this is constant, this is not constant, so as isotrivial as it could be. But even that's not a fix. So let F over Q be a real quadratic field. Let T split in F. Now, let A over C, T is in characteristic P, remember, be a family of abelian surfaces with Rm by F. And of course, I want it to be a non-ordinary family. So now there's like, no behavior of that sort. Even this has a property that there's only finitely many points at which the Picard rank jumps, and indeed those finitely many points will again be super singular points. Okay. There's something going on over here. Makes the statement a little delicate to state and makes the proof harder. So I will eventually state a theorem, and also I will either sketch a proof or at least try to convince you that there's obstructions that need to be surmounted that don't exist in the CAD0 case, or even the mixed CAD, or even the ordinary case, and briefly sketch how we surmount these obstacles. But first, before doing any of that, let me set all these results in the context of intersection theory and Shimura varieties. So as we learned from Chris's talk, unlikely intersections are just incredibly hard to understand. So the next thing is to perhaps try to understand just likely intersections, which are easier. And all these statements can be set in the context of just likely intersections of Shimura varieties, not just in characteristic 0, but also in mixed characteristic and in characteristic T. So let me just set up some Shimura varieties notation, and apologies in advance, I'm going to be very fast and loose with level structure. We'll sweep all those details under the rug. All right. So here's the setup. So V over Q will be an M plus 2 dimensional vector space. M is always going to be at least 1. And eventually, not now, but eventually, M will be even. And be twice another number, little m. This is going to be a symmetric bilinear form, non-degenerate on V. Sorry, I should have said something. For all of this, we can't deal with P equals 2. And in fact, for many of these theorems, we need P to be at least 5. But 5 onwards, everything is true. the abelian surface results are true for 3 onwards. Nothing is true yet for 2. Though we expect the results to be true, but we can't prove anything for 2 in the function in the capital P case. And I'm going to assume that the real signature is m comma 2. Okay. Now let G be the G-spin Shimura variety associated to, sorry, let G be the G-spin group associated to this quadratic space. There's a natural Shimura datum coming from associated to G, and that's going to give rise to a Shimura variety that I'm going to call S. And we call the Shimura variety S. You can also look at just the orthogonal group associated to H. And the Shimura datum on G will give you one on H just by mapping from G to H, so G maps to H. Let's call the Shimura variety on H S prime. And so we have a finite Picard map from S to S prime. And the Kuga-Satake construction maps S to AG for some big number G. G is loosely going to be 2 power m plus 2 or some such thing. Yes.
Everything is defined over Q.
Everything is indeed defined over Q. Thank you very much. Absolutely. That's right. The reflex field, all of that is going to be Q. Okay. And the nice things about such Shimura, and these are the Shimura varieties that Ruofan mainly spoke about. One very nice thing about these Shimura varieties is that they admit families of special divisors. So by that I mean there's sub-Shimura varieties, a family of them that are divisorial. And these are all going to be Shimura subvarieties. These are all going to be Shimura varieties in their own right, associated to a quadratic form with where the vector space has dimension m plus 1, and now the real signature will be m minus 1 comma 2. So these are also Shimura subvarieties of the same sort. Okay, let me make a few quick remarks. The first one is that all these Shimura varieties also capture the K3 world. If you were to look at the moduli of polarized K3s, where you have a fixed polarization of degree D, or in fact, if you were to look at the moduli of polarized K3s, where you have a polarization lattice, which is positive rank, then that will be parameterized by such Shimura variety of appropriate dimension. And these special divisors will be the Noether left-edge loci. For small values of n, you get Shimura variety is associated to symplectic groups by using exceptional isomorphisms between orthogonal groups and symplectic linear groups for small values, for small rank. So if M is 1, and if your quadratic form happens to be split, then your Shimura variety is just going to be the modular curve, and your special divisors will be CM points. If M is 2 and your quadratic form is split, then your Shimura variety will be product of two modular curves, and your special divisors will be modular curve sitting inside E1 plus E1. And if M is 3 and your quadratic form is split, then you get the moduli of abelian surfaces. And Z naught of n, the Z of n's are the locus of points admitting, well, let's just say these are going to be Hilbert modular surfaces. And Hecke translates of A1 cross A1, depending on what n exactly is. Okay. Now you can ask the same question. You can start off with a map from a non-constant map, a non-constant holomorphic map from the open unit disk to your S, and you can ask for the locus of points which map to some special divisor. And Ogusio proves that, so that's a just likely intersection question. And Ogusio proves that that set is in fact dense. All right. And Salim actually proves stronger and really beautiful equidistribution theorems in the setting when you replace D by an algebraic curve. But all happening over the complex numbers. Sorry.
No, U, I, and Z.
You switch the S to the
I, okay, so transposition. Thank you. Thank you very much.
So
Yes.
little f is the finite map from S.
Oh, sorry, I'm sorry. F is a map from D to S, and you're pulling these back, and that's going to be dense. Thank you.
Is it true that if you take the n together with standard space of all bounds, this will be dense in the projective tangent band?
That's a great question. I think the answer is no, because now that's going to be codimension 2 question. Now you're asking for a codimension 2 intersection. I think the answer is going to be no. That's a great question. Yeah. At least if you were to work in the algebraic case, then it's no. I would imagine the truth is that it's no here too. Thanks for the question. Okay. So, the way all the K3 theorems were proved is actually by proving arithmetic analogs of this theorem, where you work with an orthogonal, where you work with the G-spin Shimura variety, you work with these families of special divisors, you work with an arithmetic curve mapping to your Shimura variety, and you show that that arithmetic curve intersects these Noether left stretch loci at infinitely many points. You do this both for a curve that looks like spec OK 1 over n, and also for curves that are like curves over a positive characteristic finite field. So let me just really quickly say that in order to make sense of that, you need all of this to have integral models. They do have integral models by work of Kissen. In fact, they have smooth integral models by work of Kissen when your V admits a Z lattice that P doesn't divide the discriminant. And I think by work of Keithley Madhupusi as well as by work of Pappas for Hilbert modular surfaces, even if P does divide the discriminants, you still have nice enough models. You have flat and normal models. All of that is enough to get models of all of this data over Z, and therefore also over ZP, and therefore also over FP. So let me just state theorem. Okay. So yes. Sorry. So I'm saying right now C is just an arithmetic curve. So it could either be spec OK or it could be some curve over FQ. So if it's over FQ, then I want the image of C inside S to intersect the ordinary locus. Just the image. Exactly right. Yeah. You're right. There's not a condition on the Jacobian of C. It's a condition on the image of C. That's exactly right. Thanks for the question. Okay. So now, before talking about what goes wrong if you're not ordinary and why it goes wrong, and how any of this is proved, let me just rapidly, let me state two applications of the characteristic P theorem.
Again, what is the you said Noether-Lefschetz, but how do you define the Noether-Lefschetz? What is N here? It's just in one word.
So suppose your K3 admits an extra line bundle with self-intersection N, then it lies in Zn.
Okay.
So
Okay. So
thanks for the question.
Yeah, okay. So
Exactly. It jumps, but with.
No, I know. Thank you.
Great. All right. So if you start off with any Shimura variety mod P, let's assume it's at a good prime. Let's perhaps also assume that it intersects the ordinary locus of AG. So I'm working in the Hodge-type situation. You can start off with an ordinary point. You can look at the prime to P Hecke orbit, and you can ask for whether it's dense or not. If your point is not ordinary, then it structurally cannot be dense. Chai note proves that if your Shimura variety is AG, then the Hecke orbit of a Chai proves that if you start off with AG and you take an ordinary point, then its prime to P Hecke orbit is dense. Conjecture that seems the case if you work for any arbitrary Shimura variety. And this theorem, in this case, proves that conjecture for deep-end Shimura varieties. So let me sketch why. So this is the ordinary Hecke orbit conjecture. So let X be a point in an FP bar valued point of your Shimura variety. I'm going to assume it's ordinary. Let Y be the Zariski closure, capital Y be the Zariski closure of the prime to P Hecke orbit of X. We want to prove that Y is everything. Because it's the Zariski closure of the whole Hecke orbit of a point, it's also going to be closed under like if you were to take y and if you were to hit it by some Hecke operator, you're going to end up with y. So y is going to be stable under Hecke correspondences, practically ones at least. All right. So well, now it's easy enough to show that this set is going to be finite precisely when your point is super singular. So you want to prove y is everything. At the very least, you know y is positive dimensional, so it contains the curve, contains a generically ordinary curve. So let's pick C contained in y, and we can assume that C intersected with the ordinary locus is non-empty. Fine. Now, this theorem tells you that there's infinitely many points on C which lie in some special divisor. In particular, there's an ordinary point of C that lies in a special divisor. That's the only place where we use infinitude. So let's now look at the Hecke orbit of X1, but not for all Hecke operators coming from S, but for the subset of Hecke operators induced by the sub-Shimura variety Z of n. That's a smaller set.
Sorry, did you be using this as Zn as covered?
Sorry, so Z of n, so you've got a point in Z of n. That's a smaller Shimura variety. Instead of looking at all isogenies, I can look at isogenies induced just from that smaller Shimura variety.
Sorry, maybe I didn't. Is it the case that the Zn's collectively cover the Shimura variety? Or
no, it's not. No, it's not. It's not. Let me just say no. It's a bit subtle when this has odd dimension, when your S has odd dimension. But yeah. Okay, so now you have the setting. Now by induction, you know, let's say that you know the Hecke orbit conjecture for G-spin Shimura varieties of smaller dimension. So you know that this thing is going to be dense in Zn. And that tells you that your Y has to contain Zn. Well, okay, but it's easy to prove that the Hecke orbit of a special divisor is everything, and so you're done. So that's how you deduce the Hecke orbit conjecture for G-spin Shimura varieties from here. I should say that since this has been done, Elaine student Marco D'Adazio has proved the parabolity conjecture, which is an extremely powerful and useful conjecture about relating the monodromy of F isocrystals and overconvergent F isocrystals. And using that, they've proved the Hecke orbit conjecture in far more generality. With Paul Van Hoften.
Can I ask a question on Kejio-Gizos theorem? So in the holomorphic situation,
Yes.
is that Zariski dense or is that strongly dense?
It's a holomorphic dense.
Holomorphic
dense, and Salim actually proved equidistribution theorems when your D is a complex algebraic curve mapping to S.
Okay, thank you very much.
Right? And another application, and this application is due to Daniel Bragg and Ziquan Jiang, they prove a Naranov-Shafarevich criterion for K3 surfaces defined over local fields.
Using your result. As an application of your result?
So not as an application of this theorem, but as an application of the Hecke orbit conjectures that we prove for oddness. So in fact, what they prove is that if you start off with a K3 surface over a local field having ordinary reduction mod P, start off with a K3 surface over a local field, assume that the analytic monodromy is unramified. That means the Kuga-Satake has good reduction. Suppose the Kuga-Satake is ordinary, then they prove that up to replacing your local field by a finite extension, then your K3 also has good reduction. And Yeah, so it's a very nice theorem. And in fact, the point is Ziquan just develops a theory, Ziquan and Daniel develop a theory of isogenies between K3s. So you can always pass to an isogenous K3 which has grid reduction because your Hecke orbit is dense. So now you land in a locus where your point has grid reduction. But then if that has grid reduction, then anything isogenous to it, they can prove also is a K3 surface. So that's the theorem. That's a proof. And now with Paul and Marco's theorem outside the ordinary locus, this holds just in general, they don't need any ordinary reduction assumptions. All right. Okay, let me pause the questions while I drink some water.
Is it good?
Sorry? It's really good, yeah. I made it myself. All right. Okay, so now, now what happens when you're not ordinary? Because I should get there at some point. Fine. So the counterexamples that I sketched out have the following property. You look at, okay, so let me give the counterexample, let me explain the counterexample in the setting of a Hilbert modular surface where P is split in the field that you have real multiplication by. And this is a mod P object. Now, because P is split in the real quadratic field that you have Rm by, you have 3 Newton strata. One of them is the ordinary locus. One of them is what people call the almost ordinary locus. And then the last one is a supersingular locus. Well, as it turns out, this almost ordinary locus, it doesn't intersect special divisors except at supersingular points. Now, let's call this n bad, n for Newton, and bad because you'll see why. If you look at n bad intersected with z of n for any n, this is always going to be contained in the supersingular locus. All right, now if we take any curve that's generically in this locus, then of course it's only going to intersect these divisors at a finite set of points. Okay. Some more quick setup to show that this is not an isolated phenomenon. Let me quickly say that if you were to start off with a Hilbert modular surface associated to a field F, where F is inert at P, then you have just 2 Newton strata. You have the ordinary and you have the supersingular, and the supersingular locus is a curve, not a point, not a finite set of points. And so you have one less Newton stratum, and that's because the signature of your group or of your quadratic form at P is not the split one. So there's this dichotomy that keeps persisting throughout all these theorems. All right, so there is an F crystal call it V Chris. This V stands for this V induced by this vector space V on your Shimura variety mod P. Now, let me put this over here. This crystal, after inverting, this crystal maps to the endomorphisms of H1 Chris of the Kuga-Satake abelian scheme on S. Fine. This contains This contains all the endomorphisms of A, of course. Now, for any point x on your Shimura variety, just define Vx without the blackboard to be the intersection of these two things.
You didn't define the first one.
No, I didn't define it. I'm not going to. I'm sorry. But think of it as, okay, just think of it as H2 Chris of the family of K3 surfaces.
Oh, okay.
Yeah. Okay. But stay twisted down by one for slope reasons, but yeah, whatever. Great. All right. Now, well, the way you test whether or not a point has a special divisor is to ask whether this set is empty or not, this lattice is empty or not. So your x will lie in Z of n if and only if Vx is non-empty. Let's put the union over all n is non-zero. And in fact, your Vx by construction has a quadratic form, which is positive definite. And you can further define this to say that x is going to lie in Z of n if and only if there's an endomorphism in Vx whose quadratic form evaluated in itself is n. Okay? All right. Now let me, okay, so in particular, if your point happens to lie in Z of n, then Vx has to have a non-zero vector. That means that the Frobenius slopes of Vchris x, well, you have to have at least one slope that's zero. All right. Now your Newton stratification, your Newton strata defined by what the Frobenius slopes at various different points are. Okay, so now what are the Frobenius slopes of crystals as you vary across points? Your Frobenius slopes are going to be constant in every Newton strata. In fact, the Newton strata are defined by these Frobenius slopes. So if you're ordinary, here's what your Newton polygon looks like. There's going to be one slope of -1. There's going to be a bunch of slopes of 0. And in fact, how many are they going to be? There's going to be n slopes of 0, and then there's going to be one slope of 1. So this ordinary, then every other thing, let's call the next one almost ordinary. It's going to have one slope of -half, m minus 2 slopes of 0, and then one slope of +½ so on and so forth. Now, now let's take two cases. You have the global V that defines for your Shimura variety. If this is split, or rather if this is not split, then the Newton Saturn that contains the supersingular locus as a codimension 1 divisor is going to look like this. I'm implicitly assuming that m is now 2n. So then this is going to be 2, this is going to be -1 over m, this is going to be 1 over m. And this only exists if your space is not split. If your space, so this corresponds to the case of an inert Hilbert modular surface. If your space is split, it will contain the Newton stratum, but it will contain a further Newton stratum that looks like this. In particular, points in this Newton stratum cannot lie in any set of n. Because if they did, then you'd have a slope zero part, but these don't have slope zero parts. I should remark that the supersingular Newton stratum is just something which has all its slopes zero. All right. Okay, so then as soon as the Shimura variety is even dimensional and contains and has the property that at P it has this the signature of your quadratic space is this, then this will be a Newton stratum, and this cannot contain any points that lie in Z of M for any n. So the intersection of the closed Newton stratum with special divisors is always going to be only the supersingular locus. And so whenever you're in this case, you just can't hope to have your Picard ranks jump at non-supersingular points. Now there's also similar phenomena that can happen when you work with restriction of scalar Shimura varieties. I don't want to go there because like half an hour behind where it should be. I have till 4, right, Ben?
Half past, yeah. Oh, half past 4, no.
Yeah, no, can't keep Ben away. Yeah, can't keep people away from cookies. So let me say that if you're contained in a restriction of scalar Shimura varieties, whether it's orthogonal or unitary, then the generic Kuga-Satake abelian scheme will have more endomorphisms than for the generic Kuga-Satake over S. All right, so now let me state 2 theorems. So one of them is Ruofan alone, and here's what it proves. So let A over C be an almost ordinary abelian surface. And now the following condition is crucial, such that its endomorphism algebra, endomorphism ring is just Z and nothing more. So it has to have, if the endomorphisms can only be Z, can't be bigger, otherwise what I'm going to state is false. Then there are infinitely many points.
By the way, endomorphism over C or endomorphism?
Let's say KFC bar, KFC bar. Then there are infinitely many points P in your curve such that the specialization of A at such points is isogenous to a product of elliptic curves. Okay. So I should say that whenever
There are infinitely.
yes, there are.
Okay.
There are, exactly, there are. All right. Now, let me just say that whenever you lie in an odd dimensional Shimura variety, an odd dimensional G-spin Shimura variety, then every FP bar point will lie in ZFM for some n. This is something that you can check just by looking at the group theory of orthogonal groups. Every maximal torus. Well, if you would look at SO2n and SO2n plus 1, they have the same rank. It boils down to that. Okay. And in any case, so proving that your C intersects C of n at infinitely many points is a vacuous statement. What this theorem does is it proves that C intersects Z of n squared at infinitely many points and we vary over all n. So C intersects these special divisors, but like when you restrict to like a square class. And that's what gives you that your isogenous to product of elliptic curves. So this is a theorem that appeared in Treller recently. And The main theorem, yeah, well, the theorem that Ruofan, Ziquan, and I prove is let's call this Newton's atom n bad. Let C map to S non-constant such that C does not generically lie in either n bad or its closure, namely the supersingular locus. So if you happen to be in this case, then all I'm asking for is that the curve doesn't map to the supersingular locus. Further suppose that the endomorphism of the generic Kuga-Satake abelian variety on C is the same as the endomorphisms of the generic Kuga-Satake abelian variety on the Shimura variety. So this is like a big monodromy theorem, and we do this to avoid real multiplication, restriction scalars of real multiplication Shimura subvarieties. Something stronger than this ought to be true, but we aren't quite there yet. If this is the case, then, well, C intersects the union of all special divisors at infinitely many points. So as long as you don't lie in the only Newton's atom that automatically messes things out, and if you have this genericity assumption, so this can be weakened a little bit, but then the statement will be more complicated state. Then we prove that if you're, for instance, we prove that if you have a family of K3s with the appropriate Newton polygon, then the Picard rank will jump at infinitely many points. All right, I'm out of time, so let me stop here. Thanks for your attention.
Questions? To what extent do you actually care about being an orthogonal Shimura? I mean, obviously the particularities of the results will change, because you're saying that arithmetically you can't interpolate these strata, but for a fixed speed like the supersingularity, this Newton strata or whatever. But if you're over a fixed prime, then you can, and you have these exceptional things that show up. So if you're an arbitrary Shimura variety, you can or can't prove it. Do you have sort of conjectures about when certain Manfrottate loci will?
Oh, I see. Okay. So just to rephrase the question, are you saying that? Okay, so are you saying that are there certain? Is it just like a classification or some such thing of Shimura varieties, and the Newton strata where you know that certain Newton strata just cannot intersect a Shimura subvariety, and the open Newton stratum can only intersect Shimura subvarieties on the closure?
I guess, is that what it was? Like if you had the result, I was being more naive. You have a result like this, you have a curve mapping to your Shimura variety. You want to know when it'll have certain, like it'll set certain Hecate orbits maybe of special subvarieties or something like this.
Yeah.
Are you telling me that if you like study enough and understand how the Newton strata intersect those loci, then you'll have the answer?
Yes, except for the fact that you don't have special divisors, right? Outside these cases.
No, sure, but you increase dimensions so that things are as expected.
Yes, I'd expect what you say to be true. Proving is another question, but yes, I'd expect what you say to be true. Correct.
Questions? I have a really stupid question, so I apologize in advance. But I mean, the Picard rank jumping stuff, is that related to like some jumping behavior in the Brouwer group? And is it like
jumping behavior in the Brouwer group? By that you mean the slopes of the Brouwer group changing, or do you mean?
Well, you already know more than me, but interpret it as you will.
Well, okay, so I should say that the Brouwer group of K3s does play a role in the non-ordinary case, like very significant role. So for instance, one thing that, okay, so now this is assuming that I've spoken for 15 more minutes and then I'm talking about the end of the proof. There are some numerics that show that if like this rank 2 part somehow persists at the level of a formal curve or some such thing, then in fact you must secretly lie in a Shimura subvariety. Now that sort of stuff, in order to prove these types of algebraicity statements, you need to work with, the cleanest way to do it is by working with the formal Brouwer group. So in some sense, yes, this does show up in the proof where we need to show that certain transcendence obstructions cannot happen.
Oh, yeah.
Yes.
Anywhere the root properties of the Kuga-Satake map in characteristic P, you know.
I'm sorry?
So you need in some part of your proofs the good properties of the Kuga-Satake, but in characteristic P.
So that's actually something that Kirti Madhapusi has done a huge amount of work on, and he's constructed all these things in mixed characteristic and characteristic P. Jiang also builds on his work to prove these things. So that theory already exists. That's a great point. Yeah, we very much need that theory, but that already exists, and so we have to develop it.
Yes. Sorry, I mean, I'm still sort of digesting everything. So, but like, can you explain for the layman, like, where are you actually using that C as a curve? Like, where's the key?
So do you want to say that if we, well, I mean,
It's a question.
sorry, so Chris's question is where do we use that C as a curve?
I mean, I'm sure
There's-
all over the place, but like, where's the
The most important. Well, okay, so if you were to work with, say, a surface, and if you were to work with a codimension 2 special subvariety and try to play the same game, in our case, you're definitely going to be fine simply because you can rule the surface by curves and do it for each curve and win. Probably, yeah, this ought to work. But I'll need to double check, but this ought to work. But now if you're working in other Shimura varieties, well, okay, maybe you can prove some sort of infinitude of intersections, but now you want to prove that that's dense in your surface.
Yeah.
That's much harder, I think. In theory, all your intersections, for instance, can be contained in a proper Newton stratum. Now that can't happen in the curve without it being finite. So that's one obstruction. That's like certainly one obstruction. Okay.
Let's thank Ananth again.